So today, we're going to dive into a really simple but super powerful tool that researchers use to understand massive groups of people. It's called systematic sampling. And honestly, it's a pretty clever way to get the big picture without having to talk to every single person. We're going to break down exactly how it works. I mean, just imagine you're faced with this exact problem, right? You need to understand what 10,000 people are thinking, but you just don't have the time or the money to reach everybody. So how do you do it? How do you pick a smaller group that actually truly represents the whole? Well, this is the exact challenge that systematic sampling was designed to solve.
So what is this method really? Let's dive right into the definition and see why it's often called such an elegant, simple solution to what seems like a really big problem.
Okay, at its heart, systematic sampling is all about rhythm. It's about regularity. You basically line everybody up and then you just pick people at a fixed interval. Of say every 10th person or every 100th person. The key phrase here is that fixed interval. You'll often hear it called picking every nth member. And this is really why so many researchers love this method. Its biggest selling point is its simplicity. I mean, it is so easy to construct, to execute, and to understand, which is a huge advantage, especially for studies that are on a tight budget. You don't need any complex software, you really just need a list and a calculator.
All right, so how does this actually work in practice? Let's walk through the process, step by step, and make it crystal clear.
We'll go back to our initial problem as a running example. So, we've got a total population of 10,000 individuals we want to learn about. That's our starting point. The whole process is really just 3 simple steps. Okay, step 1, we confirm our population size is 10,000. Easy enough. Step 2, we calculate our interval. So let's say we want to survey 100 people. We just divide 10,000 by 100, and that gives us an interval of 100. So we'll pick every 100th person. And finally, and this part is absolutely key, you pick a random starting number between 1 and your interval number, in this case, 100. So if you randomly pick, say, 27, you start with person number 27, then 127, then 227, and you just keep going like that. See? Simple.
But, as straightforward as this method is, it's not perfect. Like any tool, it's got its pros and its cons. We're going to look at the bright side for sure. But we also have to talk about a very important hidden catch.
So on the pro side, we've already covered how simple it is. It also does a brilliant job of eliminating what's called clustered selection. That's where, just by random chance, all your samples end up being too close together. But on the con side, you absolutely have to know your total population size. And it's got 2 major risks. It is super vulnerable to hidden patterns in your data, and, maybe even worse, it can be deliberately manipulated.
Now, I really want to zero in on that vulnerability to hidden patterns, because it is by far the biggest weakness of this entire method. And when it goes wrong, it goes really wrong. Let's look at a hypothetical example to see just how bad it can get.
Okay, so imagine we have a big old list of different dog breeds, and they're all lined up in a very specific order for some kind of study.
Now here's the catch. What we don't realize is that there's a hidden, non-random pattern baked into this list. For whatever reason, it alternates perfectly. Large dog, small dog, large dog, small dog. Every single odd-numbered dog on the list is large, and every even-numbered dog is small.
So just think about this for a second. We're following the rules of systematic sampling. We pick a random starting point. Let's say it's number 4, which is an even number. And we choose our interval. Let's say we're going to pick every 6 dogs. What kind of dogs are we going to end up surveying here?
You'd only survey small dogs. You'd pick dog number 4, then number 10, then number 16, all of them even numbers. Your sample would tell you that the entire population is 100% small dogs, which is completely false. And this little example just brilliantly shows how a hidden pattern can totally destroy the validity of your research.
So look, the reason this all matters outside of some statistics textbook is that understanding how sampling works, and more importantly, how it can fail, helps you become a much smarter consumer of information, whether you're reading the news, looking at marketing claims, or checking out scientific reports. A bad sample leads to skewed results that can look totally legitimate on the surface. But even more dangerously, it opens the door for deliberate manipulation. Think about it. A researcher could actually structure their system, choosing a very specific starting point and interval just to get the result they want, not the one that's actually true.
And really, that's the bottom line. When sampling is done poorly, whether it's by accident or by design, the conclusion is simple. It's stark.
The results are worthless. You just cannot trust the statistics that come from a flawed process.
So I'll leave you with this question. The next time you see a poll or a study or a statistic thrown around, think about how they got their sample. Now you've got a new tool to look at data with a much more critical eye. Do you think you could spot the difference between a study that's trustworthy and one that might be hiding a fatal flaw?